Good evening, everyone. Today, as you know, our topic to start is electrochemistry. And today we will going to study NCRT Chapter 2 Electrochemistry Theory Part 7. Okay, so today is the Part 7 of the electrochemistry. So let's start. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of original creators and owners. If you are the owner and have any concern or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using the generative AI, which is experimental. So, today's objective: after attending this lecture, you will be able to describe the construction of some primary and the secondary batteries. So, today our topic is around the batteries. We will study the batteries in detail. So, these are the topics following, which we going to be covered according to the NCRT. So the first topic is the section 2.5, which is batteries. Then we will talk about the subsection 2.6.1, which is primary batteries. In this, we will talk about the structure of primary batteries, what is the structure and the arrangement of primary batteries. Then the cell reaction of primary cell. So in the primary cell, what will be the cell reaction? Then we talk about the mercury cell under this primary batteries topic. Then we will cover the cell reaction of mercury cell. Then we will cover the second subsection marked as 2.6.2, which is secondary batteries. Under this, we will cover cell reaction of the secondary battery and nickel-cadmium cell at the last. Okay, so these are the topics or the major topics which we're going to cover today. So let's start with our first topic, batteries, which is the section 2.6 marked in our NCRT textbook in the electrochemistry chapter. Under the batteries, any battery, actually it may have one or more than one cell connected in the series, or cell that we use as a source of electrical energy is basically a galvanic cell where the chemical energy of the redox reaction is converted into the electrical energy. Okay, so as I said that this is the basic definition of the cell which we have covered in the first or the second lecture of the theory part of the electrochemistry, right? So as this is saying that, first of all, let me give you a basic review or overview of the battery. So what it is saying that any battery, or in the bracket it is written that actually it may have one or more than one cell connected in the series. Okay, in the last lecture we have study or we have talked about the cell connected in the series. Okay, so battery is the name of that arrangement where the cell, either one or more than one, are connected in series. Okay, so this is basically if one cell is connected with the another cells in the series, that is referred as the battery as a whole. Okay, so any battery or cell that we use as a source of electrical energy. Okay, so cell, from the cell what we generate electrical energy, right? And the cell, through the cell the current passes. Why? Because the electrons are flowing, that's why it is generating the electrical energy by the applying of external potential. This all we have studied, right? So battery, as it is a cell connection in the series, so battery we use as a source of electrical energy, which is basically a galvanic cell. Okay, where we have seen that the chemical energy of redox reaction converted to the electrical energy. This was the reaction or redox reaction happening in the galvanic cell, where the chemical energy is converting to the electrical energy, right? So, however, for a battery to be of practical use, it should be reasonably light. Okay, because as I said that the battery is the connection, or you can say the connection of cell or more than one cell in the series. Okay, so for a battery to be of practical use, that means if you are connecting so many cells together, it should have gained some weight, right? But for the practical use of battery, if you want to use the battery in the daily life, it should be reasonably light in the mass or in the weight. Compact, it should be compact. That means you can easily carry it anywhere, and its voltage should not vary appreciably during its use. And also the external voltage that you will have to provide for the reaction happening of the redox reaction, for getting the electrical energy, that voltage should also be constant, should not vary appreciably during the use of the battery. Okay, these are the points that you have that we have to remember, or that we have to keep in mind while making of a battery or while studying of a battery. So there are mainly two types of batteries. The first one is the primary batteries, and second one is the secondary batteries. Okay, these are the two types of batteries. So let's explore, or let's study about them more. Let's first of all talk about the primary batteries, which is also our subsection 2.6.1 given in our NCERT textbook. In the primary batteries, in the primary battery, the reaction occurs only once, and after use, over a period of time, battery becomes dead and cannot be reused again. This is very important point for differentiating, or for knowing the difference between the primary and the secondary battery. So in the primary batteries, the reaction, which reaction, the redox reaction, which happens to convert the chemical energy of the reaction to the electrical energy, right? So that reaction occurs only once in the primary batteries, and when it occurs, so after a use of over a period of time of that battery, it becomes dead, it cannot be reused again. Generally it has lower capacity. Okay, so primary batteries has lower capacity. That means we cannot get as much electrical energy from the use of the primary batteries. As I said, that over a period of time these type of batteries become dead, because only the reaction occurs once. They have longer shelf life, because why we are saying that, because the over the period of time, the period of time that we are talking about, that should be maintained before at the time of battery construction, right? So we consider a perfect or a suitable period of time for the use of the primary battery, or we use a suitable time for the reaction to occur once. That's why we are saying that it has a longer shelf life, because after that particular period of time it becomes dead. So we previously already decide that what will be that period of time for which the reaction will occur, and the battery will be functional, right? So it has a longer shelf life. The most familiar example of this type is dry cell. Okay, so the primary battery example, or the familiar battery as of the primary battery, is dry cell, which is also known as Leclanché cell after its discoverer. Lec- Leclanché cell was discovered by Leclanché, named scientist, and on the name of him, this name has been derived of the cell, which is Leclanché cell, also known as dry cell. Now this is used commonly in our transistors and clocks. Okay, so transistors and clocks are the good example of the primary batteries, because you see, the battery we use in the clocks, we just put that, it has a particular period of time for which the clock work, for which the cell work, the battery work, right? And then when it become dead, all the energy gets used it, and then we throw it out because it becomes dead, right? We cannot recharge it again. The other examples of the primary batteries include alkaline, lithium, zinc carbon batteries. Okay, alkaline metal batteries, lithium batteries, zinc carbon batteries. So these are the examples of primary batteries. structure of primary batteries. Now let's see, we have talked about the definition for the primary battery and its example. Now let's see that what is the structure of primary battery, how can you divide the structure of the primary battery, or how can you imagine the different functions or the structures or the constituents of primary battery. So the cell consists of zinc container that also act as anode, and the cathode is a carbon or graphite rod surrounded by the powdered manganese dioxide in carbon. Okay, so understand. So this point can be divided into two. First of all, we are defining here the anode, that what our anode is made up of in the primary batteries, and then we are defining the cathode. Okay, that what is the cathode, what it is made up of. So in our primary batteries, the cell consists of zinc container that also act as anode. Okay, we have a zinc container. That means we have a container where zinc is filled, which act as anode in the process. And cathode we use as a carbon rod, or you can say graphite rod, which is surrounded by the manganese dioxide and carbon. Okay, powdered manganese dioxide and carbon. Okay, so this is the description of the cathode and the anode we will going to use in the primary batteries. The space between the electrodes is filled by a moist paste of ammonium chloride like NH4Cl and zinc chloride ZnCl2. Okay, now the space between the electrodes, between the anode and the cathode, they are filled, the space between the electrode and cathode is filled by a moist paste. That means moist, you can say. Why we are using moist? Moist is, we have taken the moist word from the moisture. Okay, moisture means like watery. Okay, some amount of water is present in that particular substance which we are calling as moist. Okay, so moist paste of ammonium chloride, that means a liquidy or you can say a jelly paste of ammonium chloride NH4Cl, or you can also fill the space between the electrode by zinc chloride ZnCl2. The cell has a potential of nearly 1.5 volt. Okay, so this is the you can say this is the magnitude of the voltage or the potential that the primary batteries can have, which is nearly 1.5 volt. And this you can see the figure 2.8, which is a commercial dry cell consists of a graphite cathode in a zinc container. The latter act as anode. Okay, this is the carbon rod or the cathode. This silver one rod here is a carbon rod which is acting here as cathode, right? And this cathode is in a zinc container, okay, which is acting as anode. Okay, so this is zinc cup. It is also written here zinc cup anode. This is a zinc cup, and this silvery thing is MnO2 plus carbon black plus NH4Cl paste, which is the space filling substance between the anode and the cathode. So this surrounded thing, red color thing is anode because it is a zinc cup, and this in the middle we have a rod which is carbon rod which is acting as a cathode, and this cup is a cup of zinc is acting as an anode, and the space between the cathode and anode is filled by this moist paste of ammonium chloride and the zinc chloride. Okay, this is a representation of a commercial dry cell. Okay, as I said that we will study the structure of primary batteries, and the similar type of battery or the example of the battery of primary battery is dry cell. Okay, so this is the structure of dry cell in the figure 2.8. Okay, now let's talk about the cell reaction of primary cell. We have seen the structure of the primary cell. Now let's talk about cell reaction of primary cell. So the electrode reactions are complex, but they can be written approximately as follows. Okay, so the electrode reactions are complex. Why? Because they involve the distribution or participation of the electrons in different amounts for the oxidation and the reduction process. So they kind of complex, but they can be written approximately as follows. So on the anode, you can write the reaction as zinc, because zinc is undergoing the oxidation process. So zinc going to going under the oxidation process and converting to zinc 2 plus 2 electrons. So it is releasing 2 electrons. It is undergoing the oxidation process on the anode. Now cathode have this reaction where the manganese oxide dioxide MnO2 plus ammonium ion, and they are gaining an electron and a negative charge and converting to manganese hydroxide plus ammonia MnOH plus NH3. Okay, this is the reduction process. The gaining of the electron is happening on the cathode. Now, if you want to tell the cell potential for this primary cell, you can use the Nernst equation, which is given as E equals to E naught minus RT by 2F ln zinc 2 plus MnOOH upon NH4 plus MnO2, right? So this is the Nernst equation. We have studied this before, and in this E represents the overall cell potential. Okay, this is representing overall cell potential, and this E naught is representing the standard cell potential. Okay, so E is representing overall cell potential, E naught is representing a standard cell potential, minus RT by F. R is a constant, which is gas constant. T is a temperature. F is Faraday's constant. 2 we have taken here 2 because initially we use here N. Okay, we take here N in the denominator in the Nernst equation. N represents the number of electrons which are involving in our redox reaction. Okay, so that's why here we are taking N equals to 2, because you can see 2 number of electrons are involving in the oxidation and the reduction process. Okay, so N equals to 2, and ln here will be product by the reactant. Product will be zinc 2 plus zinc 2 plus times MnOOH divided by NH4 plus times MnO2. Okay, so this will be the Nernst equation for the cell, or the primary cell. Now, in the reaction at the cathode, this manganese is reduced from the +4 oxidation state to the +3 oxidation state. This manganese from here to here going from +4 to +3. Here the manganese is having +4 charge, here the manganese is having +3 charge. Okay, so we are saying that in the reaction at the cathode, that means at the cathode and electrode, the reaction which is happening, the manganese is undergoing a reduction process where it is reducing from +4 oxidation state to the +3 oxidation state. Now, ammonia produced in the reaction, as you can see on the cathode, the ammonia produced in the reaction forms a complex with zinc 2 plus ions, because they both are at the product side. Okay, so they will combine, they will react and form a complex with the zinc 2 plus this ammonia, and to give this complex, which is zinc NH3 whole 4 whole 2 positive. Okay, this will be the final complex which you can get from the reaction of the ammonia produced on the cathode with the zinc 2 plus. Okay. Okay, now let's talk about another cell, which is mercury cell. Mercury cell suitable for low current devices like hearing aids, watches, etc., which consist of zinc mercury amalgam and as anode, and a paste of mercury oxide and carbon as cathode. Okay, so again, as we are talking about a new cell, mercury cell, we talk about its anode and cathode. So first of all, we use the mercury cell, or it is suitable for a low current devices where we either need no current or we need a very low amount of current. In those devices we use the mercury cell, like hearing aids. Hearing aids means the person which is not able to hear anything, okay, they have this natural thing. So they use the machine which is known as hearing aids, which help them to receive the sound signals, and they can then hear, right, through that hearing aids. So in the hearing aids, the mercury cell is used. In the watches, again, mercury cell is used, and it is consisting of zinc mercury amalgam, which is acting as anode, which is our anode, and a paste of mercury oxide and carbon, which is a cathode. Okay, here in the mercury cell. So the electrolyte is a paste of potassium hydroxide and zinc oxide. Okay, so basically electrolyte is a paste of the KOH, that is potassium hydroxide, and the zinc oxide. This is the figure, you can say, marked as figure 2.9 for the mercury cell. Commonly used mercury cell, the reducing agent is zinc here and the oxidizing agent is mercury second oxide. Okay, you can see it is in the circle. This is kind of the cell we used, in like in our watches too. Okay, because watches need this circular type of cells. So that is called as mercury cells, which we use in the watches. And what is its structure? If you can see, we have this structure of circle, and inside this we have red, yellow, and the blue part. This yellow part is a separator between the cathode and the anode. The blue part is a cathode and the red part is an anode. And this upper part is anode cap, okay, is called as anode cap. And this container, this thing, this upper thing, okay, this has a greater length than the anode cap. So this thing is called as cell can, okay, where everything is fixed. Yellow part is a separator, and this silver part here, okay, a slight silver part which is of the cell can, is known as the gasket. Okay, so this is the structure for the mercury cell. Now let's see the cell reaction of the mercury cell, that how the reaction has happened. So the electrodes reactions for the cell are given below. So at the anode, we have zinc amalgam, which is zinc Hg, and it reacts with the two hydroxyl ions and converts to the zinc oxide and produce the water molecule and give 2 electrons. Okay. Meanwhile, at the cathode, the reaction is between the HgO, mercury oxide, and the water molecule, and they will gain 2 negative charge or 2 electrons and become the mercury, okay, convert to the mercury element in the liquid state and also release 2 hydroxyl ions. The overall reaction is represented by, now as here the anode and cathode reaction are distributed for the mercury cell, right? Now how can you write the overall reaction? By adding these two by these two electrode reaction, anode and cathode reaction you have to add, then you can get the overall cell reaction, which is represented by zinc Hg plus HgO. That means this plus this will give you zinc oxide plus Hg, because remaining will cancel out, because the same amount of the remaining molecules will present at both product and the reactant side, so they will cancel out, and the zinc HgO, zinc amalgam and the mercury oxide will be at the reactant side, and zinc oxide and mercury will be at the product side. So this is the overall cell reaction for the mercury cell, because we are using here the mercury element, and the mercury is also we are getting in the liquid state. That's why, as the name says, it has a name, mercury cell. The cell potential is approximately 1.35 volt for the mercury cell and remains constant during its life, okay, during the entire life, because mercury cell, as we are studying this under primary batteries, and as I said that primary batteries is a single use battery because we cannot reuse it. So this this voltage, which is 1.35 approximately for this mercury cell, so this cell potential remains constant during its life, as the overall cell reaction or the overall reaction does not involve any ion in the solution whose concentration can change during its lifetime. Because what is the reason that why the cell potential is approximately 1.35 and it will going to remain constant during its life? Because the final or the overall cell reaction of the cell is not involving any kind of ions whose concentration in the solution can change during its lifetime. Okay, now let's shift to our next topic, which is secondary batteries. Okay, secondary batteries is the subsection which comes under the section 2.6. This is secondary battery, which is 2.6.2 subsection marked in our NCERT textbook. Now, in the secondary batteries, so first of all, these are rechargeable batteries. So primary battery we cannot recharge, so the secondary battery can. So we can recharge and reuse again the secondary batteries, generally having higher capacity. Okay, they can store more, they have higher capacity. Shorter shelf life, they have shorter shelf life. They have, okay, the example of the secondary batteries are lithium ion battery, nickel metal hydride batteries. Okay, so these are the example of secondary battery and some properties of the secondary battery. The first of all and the important thing is that it is rechargeable and it can be reused again, while the primary batteries cannot be. And it has generally higher capacity, it has shorter lifespan because it can discharge very soon and then you have to recharge it again, so it has shorter shelf life. The examples include the nickel metal hydride batteries and the lithium ion batteries. Continuing on this, a secondary cell after use can be recharged by passing the current through it in the opposite direction so that it can be used again. Okay, so secondary cell, first of all, secondary cell we can reuse again, that I said already. So how can we do that? We have to recharge it. How? By passing the current through it in the opposite direction, so if so that it can be used again. Okay, and whatever the direction of the electron will be on passing the current, you have to the current should also pass in the opposite direction of the electron movement, so that the current will pass and the battery will recharge again to use again, so that it can be used again. Okay, a good secondary cell can undergo a large number of discharging and charging cycles. Okay, now this discharging and charging cycles kind of determine the cell life. Okay, so a good, or you can consider a secondary cell as a good cell which can undergo a large number of discharging and the charging cycle. This cycle of discharging and charging again. So the cell which is having a large number of the cycles of discharging and the charging is considered as a good secondary cell. Most important secondary cell is the lead storage battery, which is commonly used in the automobiles and the inverters. Okay, so the most common use, that means the widest used secondary batteries is in lead storage battery, which we use in the automobiles, in our daily life, and in the inverters. Okay, if you remember, inverter is having a battery inside it which gets discharged if you use it particularly during some amount of time, and then it get discharged, and then you have to charge it again, and then you can reuse it again. Okay, so that's why the secondary batteries, uh, uh, or you can say lead storage battery, which is a type of secondary battery commonly used in the inverters and the automobiles. So it consists of a lead anode and a grid of lead packed with lead dioxide PbO2 as cathode. Now we are talking about the anode and the cathode of the secondary battery. So of the lead storage secondary battery, it is consist of lead anode. So anode is of lead element, and a grid of lead which is packed with the lead dioxide is our cathode. Okay, a 38% solution of sulfuric acid is used as an electrolyte. And here, other than the anode and cathode, we should also know about the electrolyte, right? In which, or you can say, which conform the relation, or the attachment of the anode in the cathode, by which they will attach, or by which they will interact with each other. So the electrolyte, if you consider that this electrolyte is filled here, and the two rods of one is electrode, one is anode and the another is cathode, they are dipped into it, so that the suitable movement of the electrons and the ions will happen through this electrolyte. Okay, so we should also know about the electrolyte. So 38% solution of the sulfuric acid H2SO4 is used as an electrolyte in the lead storage battery secondary batteries. So this is the structure which is marked as figure 2.10 in our NCERT textbook, and this is showing us a lead storage battery. You can see here a cuboid thing where we have anode. This blue rods are anodes. This is cathode. This one is a cathode, and these are representing as negative plates, which lead grids filled with spongy lead. And this cathode color is red, right? So here in the vertical, the red color thing is positive plates. Okay, they are basically lead grids which is filled with lead oxide. And here the yellow part, which is present in very much amount, this is 38% sulfuric acid solution, which is acting as a electrolyte here, in which the anode and cathode both are dipped, in which both are arranged themselves. And we have the construction of, or the structure of, our secondary battery, which is the lead storage battery. Okay, these are the type of batteries which we use in our homes, in the inverters, or in the industrial usage, or also in the automobiles. Okay, so lead anode and a grid of lead which is packed with lead dioxide, as they will act as cathode. Okay, so this is kind of the structure of the lead storage battery. Now let's talk about the cell reaction of the secondary battery. Okay, now if we have talked about the secondary battery there and its structure, let's talk about what is the cell reaction which is going on inside the secondary battery. Now the cell reactions when the battery is in use are given below. Now when the battery is in use, that means the battery is charged. Okay, it is not discharged. So when the battery is in use, the cell reactions which is happening are given below. At the anode, the lead in the solid state will attract or will gain some sulfate 2 negative ions in the aqueous medium, which is of the electrolyte, 38% solution of H2SO4. Right, so basically we have H2SO4 electrolyte, which will from which we will going to get 2H plus SO4 2 minus. Right, so these SO4 2 minus will react with the lead, which is anode is made up of, and they will form the lead sulfate, that is PbSO4, and 2 electrons. Okay, so we will also get the 2 electrons. So this is kind of oxidation process happening, where the lead is going from the normal, like neutral state, to the PbSO4. Okay, and it is also releasing the 2 electrons. Similarly, at the cathode, the other electrode present in our battery, the reaction happening at the cathode is lead oxide, that is PbO2, reacting with the sulfate ions and also attaching with 4 protons and 2 electrons and giving us lead sulfate and 2 molecules of the water. Okay, as you can see, at the anode and the cathode we are getting the same product, which is lead sulfate, which or maybe you can relate it with the name of the battery, which is lead storage battery. Okay, now continuing on this topic, that is the overall cell reaction consisting of cathode and anode reactions. Now if you write the overall cell reaction of the lead storage battery or the secondary batteries, that will be the sum of the, or you can say, overall cell reaction of cathode and the anode reactions, which is lead attaching or adding with lead oxide and two molecules of H2SO4 sulfuric acid, and giving us two molecules of lead sulfate and two molecules of water in the liquid state. Okay, so this is the overall cell reaction which we get from the individual cell reactions of cathode, individual electrode reactions of cathode and the anode respectively. On charging the battery, the reaction is reversed and the lead sulfate on the anode and cathode is converted to the lead and lead oxide respectively. Okay, now what will happen if the battery is charging? Okay, so when you are charging the battery, that means when the battery is discharging, try to understand, if we have a battery, okay, if we have a cell or a battery, you can consider, if it is discharging, so it has some maximum power. Okay, it is discharging means it is undergoing a process where this battery power is decreasing. Okay, so maybe 3 or 4 will remains from these 7. Okay, type of, we are just indicating, I am just taking an example to describe you. So this is full charge battery and this is half charge battery, or you can say quarter charge battery, where the battery is discharging. Okay, that means some reaction is happening from starting to the ending while the discharging process is going on, right? When it gets fully discharged, then you put it to charge it again. Okay, then you charge it, or you can say recharge it again. Okay, what will happen, this state, you have to go from this state to this state, right? Or you can also say that firstly you have to go from this empty state to this median state, and then you have to go to the final state, which is the fully filled battery. Okay, that means whatever the reaction you had seen, or whatever the reaction has been done while the discharging process of the battery, that should be reversed while the charging of the battery, right? So that's why it is written that on charging the battery, the reaction is reversed, and the lead sulfate which we are getting on the anode and the cathode, as I said, as I point out, that at the anode and the cathode, at both the electrodes, we are getting the lead sulfate. Okay, so this lead sulfate is converted into the lead, it is converting into the lead and lead oxide when the charging process is going on. Okay, because the reaction kind of reverse, and whatever you will get the product in the discharging process, it will get reversed, it will become reactant, and the product is which you will get while the recharging process is the reverse. Okay, so at the anode you will get from lead sulfate to lead, and at the cathode you will get from lead sulfate to lead oxide. Now during the charging process, this will be the reaction which will going to happen, which is 2 lead sulfate which you are getting at the anode and the cathode, and the 2 molecules of the water which you are getting in the overall cell reaction of the lead storage battery. This will get reversed, and these 2 products which you are getting as a product in the overall cell reaction, they become the reactant, and they will going to dissociate into the lead oxide and the sulfuric acid. Okay, so reaction gets reversed during the recharging process. Okay, now let's talk about our last topic, which is nickel-cadmium cell. Okay, it comes under the subsection of 2.6.2, which is secondary batteries. So this is nickel-cadmium cell. Another important secondary cell. Okay, this is a secondary cell because we are studying it under the secondary batteries topic. So another important secondary cell is nickel-cadmium cell. Nickel is Ni, cadmium is Cd. Okay, NICD cell, which has longer life than the lead storage cell, but more expensive to the manufacturer. Okay, now you can understand that the quality is good for the nickel cadmium cell because it is having a longer life, which we want from the batteries. Why we need a battery? Because we want to store the charge somewhere, or we want to store the cell somewhere to prevent its energy so that we can further use it in the future to convert the chemical energy to the electrical energy. Right, this was the main focus. But if the battery lifespan is short, if it gets discharged very soon, I am talking about in the case of secondary batteries, then what will happen, that kind of battery will considered as uh, you can say cheap, right, or less used. Okay, so another important secondary battery we are talking about is nickel cadmium cell here, which has a longer life. That means it can be reused or used again and again at a longer period of time. So it has a longer life than the lead storage cell. Okay, if you compare it with the lead storage cell, nickel cadmium cell has a longer life. But what is the reason that why we are not using the nickel cadmium cell in our daily uses in the automobiles or in the inverters? Because it is more expensive to manufacture the nickel cadmium cell than the lead storage cell. That is the main reason. We shall not go into details of working of the cell and the electrodes reactions during the charging and the discharging. So we will not go into the details of that what is the working of cell and the electrode and what is the reactions during the charging and the discharging. The overall reaction during the discharge is, so the overall reaction means whatever the reaction which is happening during the discharge. Okay, we just saw the charging during the charging reaction, right? Now the overall reaction during the discharging process. That means we have a full charge battery and it is going to discharge. That means its energy is going to consume or decrease. Then this will be the reaction in the case of nickel cadmium. So cadmium in the solid state reacting with 2 NiOH whole thrice in the solid state, converting to the cadmium oxide plus nickel hydroxide plus the water molecules we are getting. Okay, so this is the reaction which is happening, or you can say overall reaction during the discharge of the nickel cadmium cell. So as the name says, nickel cadmium, that means in this cell we are going to use cadmium and the nickel, and both we are using here. This is the figure, which is figure 2, marked as figure 2.11 in the NCERT textbook, which is a rechargeable, which is a diagram of rechargeable nickel cadmium cell. Rechargeable, why we are using? Because it is a secondary battery. Secondary batteries can be recharged and can be reused. So the rechargeable nickel cadmium cell in a jelly roll arrangement and separated by a layer soaked in moist sodium or potassium hydroxide. Okay, as you can see, we have this positive plate, the silver one, the yellow one is a separator, and the blue one is a negative plate. So we have layers which is soaked in the moist sodium or the potassium hydroxide, and this is a kind of the structure for our rechargeable nickel cadmium cell. You can also see that this is kind of a tricky structure for a cell where different vertical layers are arranged one by one, and there is a positive plate, the silver one. The yellow part is a separator which we are using continuously in the cells to separate between to make the separation between the anode and the cathode. So this is the separator in the yellow part, in the yellow plate, and the negative plate is colored as the blue, right? So this is kind of arrangement. You can see separator, then silver positive plate, then yellow separator, then blue negative plate, then yellow separator, then silver positive plate. Okay, so positive separator, a negative separator, okay, positive separator. So this is kind of arrangement in the form of plates, in the vertical plates in the rechargeable nickel cadmium cell. Okay, and this is the reaction or the overall reaction during the discharging process of the nickel cadmium cell. And as I said, that nickel cadmium cell we study under the secondary batteries because we can recharge it again and use it again, but because it is more expensive to manufacture as compared to the lead storage cell. Meanwhile, it is having a longer life than the lead storage cell. Still, we are not using it in our daily uses because it is expensive to manufacture. Okay, so this is all about the nickel cadmium cell. Okay, now okay, so someone said that I have 2 weeks backlog in all subjects. PCM, please tell me to finish it. Okay, yeah. So if you have any kind of backlog or any kind of doubt, we have some time. You can uh, type it in the chat. And here someone is saying that they have 2 week backlog. So basically, if you are having backlogs in all the subjects, including physics, chemistry, and mathematics too, then you have to start to or you can say that you have to restart again, okay, to understand the subject properly, including 11th and the 12th class. Okay, that means the concept are missing. You are not understanding the concept. You are not practicing the questions properly. Basically, the concept understanding is poor. You need a lot of practice for that. So like try to watch our lectures or the videos we are uploading, and the lectures we are try to teach you all the points, the sections according to the NCERT in detail. So try to learn that, or the try to focus in learning the concept, that what the concept is saying, what the topic is saying. If you are talking about the cell, then what is cell basically? Okay, we are talking about cell, we are talking about its reaction, whatever. Okay, but if you are talking about a cell reaction, you have to firstly understand that what is redox reaction. Okay, because that type of reaction is happening in the cell. Okay, then how can you represent the cell? Okay, so try to understand that you have to know about the basic concepts, then you can go to the solving of the questions, or practicing of the questions, previous year questions, or CBSE PYQs. We will also going to catch that in this lecture series for each of the chapters. Okay, so try to concentrate and try to follow us also during the lectures. If you have any doubt, you can chat with us in the chat box. Okay, and okay, anyone, if you want to ask anything, we have still some time. Yeah, from this chapter, I would say there will be many numerical questions that can be asked on the basis of, like, in the previous lectures we have studied about Nernst equation, right? So Nernst equation is very important. On the Nernst equation, there will be many numerical questions. You can also check that in the previous year's questions. Okay, whether in JEE, NEET, or CBSE. So they were repeatedly asked the questions on the Nernst equation especially, and some other topics also, like type of batteries also. And yeah, on the secondary battery there is not that much numerical type of questions, but they can ask the concept wise questions, like the short answer type question, the long answer type question, like they have given some kind of name of the cell, and they will say that tell the structure of the cell and cell representation and the cell reaction for both the cathode and the anode electrode also. Okay, so how can you check the PYQ for the J means? So basically you can search it either on the Google, okay, or you can also visit the SATHEE website for that. And on that, in the JE section, you can find everything for the JE means and the advanced both. Okay, that how. And you can also practice there. You can also take the PYQs or the mock test there for the practicing of the JE means PYQs. Okay. Okay. Okay, so that's all for today's chemistry session. Okay, and thank you very much for joining us.